You can start whenever you want, Nima.
Thanks. Well, yes, we are going to talk about storing and protecting data on the Internet Computer Protocol today. I hope that this is going to be an informative lecture, and I hope that you learn a lot of things from this lecture. So I'm going to start a little bit about myself. I'm Nima. I'm a tech lead at Fleek. I have worked on dApp as a product of the psychedelic DAO, and also I have worked on Dank and Crown's NFT collection. I'm currently working on a governance framework for ICP in the psychedelic DAO, and that is something that I'm very excited for, and I think we are going to release it in the next few months. Some other fun facts about me is that I love literature. I love the works of Shakespeare and Dostoevsky, although my mother tongue is neither English or Russian. I'm Persian. I love cinema and I love the works of Kubrick and Hitchcock. So if you ever want to talk about cinema, I'm always there. And I also love philosophy and history. That's how I spend most of my time when I'm not coding and when I'm not learning about technologies. So with that being said, I'm going to start the talk on data, because one of the most important things in decentralized applications is data. And the same goes for Web2 applications, because data is everything. For programs like dApp or CAP, data is the most fundamental and the most important thing that you can find, because CAP essentially works on history. And Dank, if you're familiar with these services that I'm mentioning, you know that Dank is basically a ledger, a bank that records transactions. It says who spent how many cycles, who moved how many ICPs to another person. So without having those records, this bank can't work. And the same goes for dApp. dApp is a collection of registries, like a registry for NFT collections. So people, if people want to include their collection in Plug or other dApps that have been integrating dApp, they can just submit a form proposal to dApp and say that, hey, this is my NFT collection, and if you want, I want this collection to be visible in all of the apps that integrate dApp. So dApp takes some metadata like the URL, the asset type, the name of the NFT collection, the description of it, and all other things like that, and starts adding it to the registry itself. As soon as it's added to the registry, all of the dApps that have been integrating dApp can just simply show your NFTs. So as you can see, data is very important in the Internet Computer Protocol, because all of the dApps that I just mentioned wouldn't work without data. And one of the most important things about data is that if we lose it, we are not going to simply get it back. And that's like the whole point of this lecture. We need to find the most efficient way to store data, and after that try to save this data from malicious actions and getting erased on the protocol. So that's what we are going to focus on today. And I'm going to start with this simple flowchart. As you can see, this is dApp. This is a very simple flowchart, and that is an admin of dApp who wants to add a new canister to the registry. So the admin calls a method on dApp and says that, hey, I want to add this new NFT to the registry. And dApp says that, okay, I see that you're an admin, so you have the proper authorization, and I can see that the metadata is correct and I can validate them. So I'm just going to add them to the registry. And what I get from dApp is a response that says, okay, the canister has been added. So no problems there. But one thing to consider here is that we don't know how dApp stores that data. If you look at the open source code of dApp, you probably learn how it works. But when you're designing your own dApp, you probably won't be able to actually uh, design the system of that smart contract canister without taking inspiration from other dApps that are already open source on the internet computer. So there are a few options that we have for storing data on the internet computer protocol. One of them is using hash maps and B-tree maps. I know that some of you are familiar with these concepts. We are just going to go over them today and try to get a little bit more in depth with these concepts. And I'll try to explain what is the exact difference between hash maps and B-tree maps. The next way that we can store information and data is by creating an assets canister. Assets canisters are very effective in a sense that they can hold a large number of assets with a large file size. Like the fact that the current canisters is going to hold about 10,000 MP4s. That's just something that we need to take care of, because that is going to be an incredibly large number of files with large file sizes. So that's where we use assets canisters. Right now, I can say that the Crown's NFT collection is divided into 3 canisters. One of them is the main canister that contains the information of all of the Crown NFTs, and there is the assets canister that contains the MP4s, and there is also another assets canister that contains the other half of MP4s. And the reason that we have divided the collection in this way is that it is the most efficient way that we could design. We could find. We couldn't just simply try to store 10,000 MP4s in one canister. That wouldn't be feasible. So that's when we use assets canisters. And one other way that we can store information is by using certified assets canisters. So if you start to think about how internet computer actually works, or any other blockchain for that matter, you will notice that it is a little bit different from the traditional web. In traditional web, you just try to go to google.com and you will trust the response that you get from google.com by comparing the hash and the public key. You will just know that the Google is sending the right response and no malicious actions has been taking place. But in the Internet Computer Protocol, you have to trust the public key, but inside the network, if a subnet is doing malicious actions and is trying to change the information, that subnet won't have that subnet's information won't reach enough consensus across the network. So you probably are not going to see a malicious action take place inside the network of subnets inside internet computer. And the certified assets canisters are exactly what we need to make sure that all of the responses that we are getting from certain canisters are correct. They are validated. We can trust them, and we can try to build other dApps around them. Talking about certified assets canisters is going to take a while. I'm probably not going to focus on them much today, because even an introduction about certified assets canisters is going to take at least 30 minutes. And I try to introduce it to you as much as possible. But after the lecture, I'm going to share a few links with you just to give you some resources about certified assets and assets canisters, so that if you're interested, you can just watch those videos and read those documentations and try to learn about these canisters as much as possible. So the first step is hash maps and B-tree maps. We are going to talk about maps. I'm going to stop sharing the presentation right now and try to share the share my screen because I'm going to go over some of the code that I have written last night for the presentation. It's very simple. It is not very complex. I'm going to talk about hash maps, B-tree maps, and upgrade the scripts. So I'm going to share the URL for that GitHub repository in the chat as well. So I'm going to just stop sharing the screen for a moment. This is the URL. Oh, okay. I can see that in the chat. Ashen has said that there was a lecture earlier this week about certified assets cancers. Okay, I didn't know about that. And it's a good thing that we are not going to talk about the certified assets that much in this lecture. But I'm going to share those links with you anyways, just to make sure that you have as many resources as possible if you want to learn more about certified assets. Okay, so this is the repository that I was talking about. This is a repository that I just created for the sole purpose of sharing with you in this lecture. I'm just going to tell you that this is a Rust canister, and although I know Motoko, I don't use it anymore. I just wrote a one canister ever since I started working on internet computer with Motoko. And after that, I just started using Rust because there were more resources with Rust. So there is a README. It is not much, honestly. We are going to update the README in the lecture, so you don't need to read it exactly, and you probably know how to run a canister. I'm just going to show you the structure of the code right now. There is a dfx.json file that for Rust canisters has a little bit different structure than Motoko canisters, because as you can see here is the name of the canister. This is the build command that we are going to use for the canister. As you can see, it's a node build.js lecture. So you might be wondering what is build.js. Well, it is a JavaScript file that I've written for just optimizing the is going to generate a canister. The location of the candidate. We are going to write the candidate ourselves, so it is not there right now. This is the location of the WASM. As you can see, it is under the release directory in the target WASM32 unknown directory. So when you try to build the canister yourself, you'll probably see that there are two WASMs in this directory. One is lecture.wasm and the other is lecture-opt.wasm. -opt is the optimized version of the lecture.wasm file. So this is something that we are going to go over today. I'm not sure if you know about this already or not. I mentioned this in yesterday's Dev Mentor hour. So I'm just going to talk a little bit about it today too. The optimized version has a smaller file size, which can help you when you try to build bigger canisters with larger data sets. And the type is custom. It's not Motoko, because we are not going to write the code in Motoko, of course. And you can write Rust here. I've written custom. The reason for that is that I'm just trying to use the optimized version. If you want to use the unoptimized version and not use the build.js script, you can just write Rust and forget about the WASM field. And that is the basic structure of our dfx.json file. This is the build.js file I'm talking about. As you can see, it's not actually a big deal. It is just a simple, it runs a simple command. Cargo build -target wasm32 unknown with the release flag and the name of the package, that is lecture. So it runs the ICCDK optimizer CLI tool on optimized WASM, and says that the output should be named the same, but with just dash opt in the name. So this is just a simple, very simple script that we can use to make sure that our WASM is optimized. And there is a cargo.toml file, which contains a list of our canisters. We currently have only one canister. If we go to another canister, like another project like that, we can see that in the cargo.toml file, we have about 6, no, it's more than 6 actually, 8 different canisters with 8 different locations. And if we have other canisters, we are not just going to add them to dfx.json. We have to add them to cargo.toml as well. So that's a tip for you. And in the lecture here, we have the code for the canister itself. We have another cargo.toml file. Here we have listed the dependencies that we're going to use in this canister. One of them is ICKit. The other is ICCDK, ICCDK macros, IC types. And these two are just for serializing and deserializing the information. So you probably already know what ICCDK is, so I'm not going to talk about it much. I'm just going to introduce ICKit. So if you're developing on Motoko, you won't need ICKit because there isn't a version for Motoko. But if you are developing on Rust, you are going to probably need to use ICKit, not ICCDK. ICKit is a dependency that is a package that we have written in Psychedelic for internet computer development with Rust. You can use it to build test cases and making intercanister calls. You can make intercanister calls with ICCDK as well, but I'm just saying that with ICKit, it's much easier because we have tried to make it as simple as possible. And we are going to use ICKit in this lecture. And this is the source files that we have. And the lib.rs file is just going to list all of our other files. So it's going to sort of import them here and use them. The first file that I had important was common types. This is something that we always create when we are trying to develop canisters with Rust. There are some types that we just use over and over in the canister. So we decide to make a separate file for those types. Here we have included the candid and candid type principal types from ICKit, and we have also included the deserialization option from the package. We have a simple structure here that is named metadata. This is a metadata that we are going to store from every canister that we add to the registry. Yes, we are going to build a registry together. It's just like another DApp registry. So actually, if you watch this lecture until the end, you'll probably know how to build the DApp registry yourself too. And you can do that, actually. You can build your own registries and try to add them to DApp later. So we're just going to store a simple string for name, a description string, and the field for principal IDs. And we are going to expect a few errors. So a user might not be authorized, might not be an admin to call add or remove methods. A user might try to access a canister that doesn't actually exist in the registry. A user can send the wrong parameters and some unknown errors that we might face. So we always add this just to make sure that if something happened that wasn't, in these 3 other error fields, we can just use unknown to add it there. So that is a very simple file. The next file that we are going to see is the hash map file, and we are going to technically start right here. So I don't know how many are you actually building on Rust right now. How many of you are actually trying to build on Motoko? But this lecture is going to be hopefully beneficial to all of its audience. because what we're going to talk about today is not actually just about Rust. You can use the information in Motoko as well. So you can use hash maps, B-tree maps, upgrade the scripts in Motoko as well. You don't have to, you shouldn't think that just because we are writing the code in Rust, we are not going to use the information. We won't be able to use the information in Motoko. No, that's just wrong. You use hash maps and B-tree maps in Motoko all the time. So here we have imported comment types, management, and we are going to go over management later. In management, we assort the list of admins and all that sorts of things. And here we include the hash map. So what is a hash map? I'm going to just say that hash map is a map with key value datasets that is not sorted in any way. So if you add 1, 2, 3 as key values to a hash map, you will notice that the first item might not be 1, might be 2, and after that 1 and then 3, because it is not sorted in any way. But if you decide to use B-tree maps, that's a different thing, because with B-tree maps, everything is sorted and they have different use cases. For example, in all of the app registries, we are using hash maps except one, and I'm going to show that to you later. And I'm going to show you exactly why B-tree maps are just as important as hash maps. So here we just create a hash map database. The key value is, of course, a principal, because we are going to take the principal of a canister, and after that, we are going to assign a certain metadata to that principal. So this is the key, and this is the value. And here we have the implementation of the database. The implementation contains a few methods itself, and we are going to call these methods outside of the implementation, inside the methods that are going to be called by admins and users from DFX. So we just, I'm going to talk about archive and load later. Let's just start with add. We just simply take the mutable self status of the database, and we try to insert the canister ID, principal ID, and the metadata. It's actually not, as you can see, it's not very different from Motoko. The syntax might be different, but it's just the same concept. And the same goes for remove. We just check if the key is already there. If it is already there, we just remove it. If it is not there, we return a new error because the item wasn't found. The item isn't inside the registry. So we can't actually remove an item that isn't already there. We're just going to say that the item doesn't exist. And then we have the get method. This simply just returns the metadata if it already exists in the database. As you can see, it's an option. Options mean that there might be a value and there might not be a value. So if the metadata doesn't exist, the canister maybe doesn't exist in the registry. In that scenario, we just return null. In Rust, we write none, but in Candid, it is translated into null. So you can expect a null there, but if data is there, we just expect metadata itself. And we have the get all method, which just returns a vector of metadata, returns all of the metadata that we have currently stored in the database. And that's the implementation that we have. It's a very simple one. It is not complicated at all. And if you design your own dApp in an efficient way, you probably won't have a much different or much more complex database than we have already here. You might have certain validation fields, you might have certain new methods in the database, but the overall structure probably will look like this. And we have a few methods here, 4 to be exact. 2 of them are update methods, 2 of them are query methods. Query methods just rely onto the first response that they get from a node, but update methods wait until consensus is reached between all of the nodes, just to make sure that the data that they are getting is actually an exact one, and it is not tampered with, and it is up to date. So those are the update methods. These are going to take a lot more time than queries, but not as much as you think they would, because they can just, in my experience, I didn't have an update call last more than 2 seconds, and queries are much faster than that. So you don't have to actually worry about updates and queries in regards of their time. So if we want to add a new entry to the hash map, we are just going to take a metadata, and inside the metadata, we have the principal ID. So that's good news, because we are not going to take 2 fields. It's just 1 field. And we are going to either give an error or just OK status if everything works well. So that's what we are going to expect from this method. First, we're going to check if the canister, if the user that is calling this method is an admin. So this is a new concept here. What is an admin? You might know already about controllers. Controllers are users who can actually update the canister's code, who can actually update the status of the canister, who can remove the canisters from the blockchain, just make it stop working. But some people might not want every admin to be a controller. So who is an admin? An admin is someone who can update the information inside of the collection, inside of the canister. And this is not exactly a documented concept. It's just something that I've used ever since I started working on Internet Computer Protocol, because I just realized that we need some other identity other than controllers. So I created admins. Many psychedelic dapps are using admins these days. So that is something that you might want to learn more about. But to summarize it, they are not much different from controllers, except the fact that admins can't upgrade the canister's code. So they don't have real authorization in the blockchain. They just have authorization inside of the canister itself. So if the user is not an admin, we just return an error. We say that they are not authorized. And we haven't defined the isAdmin method here. That's because the isAdmin method is defined in the management file. I told you that we were going to talk about management later. And here we are. We have a simple public vector of principals. This is the list of our admin principals. When you deploy your canister, this list will only contain your principal ID. And as you can see, if the principal ID, if the vector is empty, we are going to panic. We are going to panic and say, hey, we don't have an admin. What is going on? This canister won't work unless we have admins. So yes, we are going to panic there, as we should. And admin method, this just takes a principal ID and returns a Boolean and says that it tries to retrieve the list of admins and tries to find out if the principal ID is already inside of the vector itself. If it is there, yes, we return true. If it is not, we return false. And here we can see that I've added an exclamation mark here. That means that we are expecting false. So if this condition is false, the return is false. We return the error of not authorized. If it is not false, it means that the user is actually an admin who has proper authorization to add new entries to the database. So we have here, if we are calling the database, we are trying to get the mutable status of that database. So if we were just going to try to return some data. We were not actually doing any computation, or we weren't trying to change the hash map itself. We would just try to get the unmutable status of it. But when we are trying to actually change the data inside of the hash map, we have to try to get the mutable variant of that structure. So we get the mutable variant, we try to call the add method. And here is the add method that we have. As you can see, it's just very simple. We are not expecting any errors here, although the return type is the same as the add hashmap method. We're just saying okay, because as far as the logical mind can answer, there is nothing going special around here. We are not actually doing something incredible that takes a lot of preparation and strong measures to consider or things like that. No, we are just trying to add a new entry to the hash map. So if this is going to go well, and we are returning an OK status. The next method is basically the same. It's a remove hashmap method, and the other one is a get hashmap method and get all of the entries. So I'm not going to talk about these three, at least right now, because they are basically the same method as this one. So I won't bore you anymore with this information because we are not going to actually use them. But right now we are going to learn more about hash maps and B-tree maps themselves. I just showed you how we can use them inside of the code, but I'm going to show you where we are going to use them and when we should decide to use a certain B-tree map or a hash map. So if we go back to dapps, we can see that we have different registries. One of the registries is an address book. So the address book registry is just a basic registry that you can use to add new contacts to. So for example, your principal ID, you can call this method, you can call this canister and say that here is another principal ID and here is the contact name that I want to use. So when I try to use my wallet, I have to every time select the name of the contact that I want to send ICPs or XCCs to, and I'll just say that, hey, this is the user that I want to send as my assets to, and Plug will say, okay, I have the name of the user, which is, for example, Nima, and I have the principal ID of the user, which is, for example, ABCDE. That's a very short one, but it works. ABCDE, and I'm going to use that as the key to find the actual principal ID for the contact named Nima. So what it does is that it tries to get the list of my contacts in the address book registry, which uses a B-tree map. As you can see, this is a B-tree map with a certain key and a certain value. The key is very simple. It's a principal, and it's actually a tuple of principal and a string. And this is where the brilliancy of B-tree maps is going to show itself. Because if we use hash maps, we couldn't possibly try to get all of the contacts of a user, because in hash map, the data would be all over the place. We couldn't sort it in any way. The hash map doesn't sort the data in any way itself. So it would be just a huge computational waste. And when we use B-tree maps, we won't have to deal with all of those problems, because B-tree maps itself tries to sort data and returns you the sorted version of the information inside of it. So when we have principal IDs and strings as our key, we can just try to edit this one. I'm not going to commit, but if we just try to copy this line and write it this way, it would be basically the same as above. So yes, if we remove this line now, this is basically the same. You see, and with this key, I'm referring to the type that is above, which is a tuple, and contains the principal and the string. And when we try to get all of the contacts of a user, we are actually trying to get all of the contacts of a certain principal ID. So if my principal ID is something like ABCDE, all of the data that the address book has of me is the ABCDE principal ID, and it doesn't want to look for a certain contact. So it is not going to look for Nima, it is not going to look for Jack, it is not going to look for Alice, it's just going to look for all of the data about my principal ID. And you might ask a question here, why don't we do it this way? We can just use principal as the key, and we can use the tuple of a string and address as the value. You know, we can just try to get all of the information that we have from this principal ID without any complexities. So that wouldn't work. The reason for that is that different people will have probably the same contact names, and we are just trying to look when we are trying to look for a certain contact, that wouldn't work. For example, let's say that I am trying to create a new contact named Jack with a certain principal ID, and my other friend is also trying to create a new contact named Jack. So this is basically the same name, and we have to make an exception here. We have to make sure that the principal ID that my friend has assigned to his Jack is different from the principal ID that I have assigned to my Jack. So we don't, when I call my contact, when I try to call Jack, I don't want to call my friend's Jack, you know, because these are two different people. These are two different Jacks with two different principal IDs. So I just want to make sure that these are different inside of the canister too. And that is the reason that we are using principal and a string as key values. And when we try to get all of the possible, you know, when we try to get all of the possible contacts that we have right there, we are just going to set the principal ID as a clone of the caller, who is me or you in that scenario. And we are just going to generate a new string. This is a little bit of, this is a fun hack that you can use in your own projects. I mean, I personally spent so much time to come up with this very, very simple structure for the project, for the address book canister. The reason for that is that back then, when I started working on the address book canisters, it was late summer. I think it was, I don't remember the month exactly, but back then there wasn't actually much development going on Internet Computer Protocol exactly. Most of the dapps that you are seeing right now, you're using right now, started developing there, right, like Plug and Dapp. So I was just trying to find what works and what doesn't. What I found worked was the fact that if I try to create a new empty string, it would be basically the minimum value of a string possible, you know, a possible string. Because when you try to create an empty new string, it doesn't contain anything. It's empty, as I just said. So it is the minimum value. And when you try to create the latest, you know, not the latest, the maximum version of a string, you are not going to just type a Z for a million times. We are coding here, so we can do better things. We have better options. We are going to generate a string from a certain character that is from the maximum possible U32 number. So here, everything in between, this is the first possible contact, and this is the last possible contact. And everything in this range is going to be for this user. How can we make sure of this? Well, we know this for sure because we are using a bittree map, not a hash map. If we were using hash map, there were no possible guarantees that all of the information between these two endpoints is going to be about the same user. But when we try to use bittree maps, we can just say it safely that, hey, yes, of course, this is the same user. We don't need to check it. We are just going to return the data. But hash maps are faster. And we are talking about the next point. I mean, hash maps are way much more faster than bittree maps. Bittree maps are very efficient, but they are very efficient for a sorted data set. They are not efficient for a data set itself. This is a sorted attribute that makes bittree maps so special. But when we don't care about sorting our data, we are going to use hash maps because, of course, that's more efficient. And that is what we are using here in the hashmap.rs file. We don't care in what order our data is stored. We don't care what is first and what is last. We just care that our data is actually being stored. So that's something to keep in mind. You might not want to use bittree maps directly, but you should always try to find a way for your program to work better with different data sets. You should try to consider all possible options that you have and think about how those options can help you with your program. How can a bittree map help you? How can a hash map help you? And after that, you will decide on what collection you're actually going to use. When I started working on the address book canister, I was using hash maps. And after that, I just realized that I have been thinking about this whole problem wrong for a long time. So I started using bittree maps. And I don't know if there's anything else to say about bittree maps and hash maps. The same is in Motoko. So we are basically talking about the concept here. The concept is the same. The implementation and syntax is different in Motoko, but the concept is the same. Bittree map is slower than hash map, but bittree map is sorted, hash map isn't. Doesn't matter that you're coding in Motoko or us. The situation will always be the same. And the last thing that I wanted to talk about was the upgrade script. The upgrade script is basically just a script that you should have if you care about your data, because a small mistake in your upgrade script can result in losing all of your information, all of the data that you're storing inside of your canister. So why do we exactly have an upgrade script? This is the new concept that we have in Internet Computer. So when I try to, contracts, go to smart contracts, documentations from Definity, and even if I search for post-upgrade and pre-upgrade methods, I'll go to this part of the documentation, which is titled Stable Variables and Upgrade Methods. So what does this exactly mean? I'm going to send the link to this documentation as well after the lecture. But what does stable variables and upgrade methods mean? So when we try to upgrade the code of our program, in the Internet Computer Protocol, we are actually reinstalling the code. So all of the information that was stored in the caser will be gone if we don't take care of it before the upgrade. Okay, so I'm getting questions in the chat. I'm going to answer them just after the lecture in a few minutes. It won't be long. Yeah. Okay, so when you try to upgrade your code, you are actually losing all of the state that you have inside of the canister. You're losing all of your contacts. You're losing all of the information that you have stored in your precious B3 map and hash map, and you will have nothing, not a single shred of evidence that there were ever a single entry in your B3 map or hash map inside of this canister, because Internet Computer is going to reinstall the code. It is not actually going to keep the data, it is going to reinstall the code. And what that means is that your current code, your V1 code, will be deleted, and the new code will replace it, your V2 code. So you don't have to actually worry about losing your data if you use an upgrade script. What does the upgrade script do? What's the magic there? Well, the magic is very simple, and it is not anything different other than what you have seen so far. It is actually pretty predictable in some sense, but it's a very novel idea. It's a very new idea in the blockchain space, because I think definitely is a first blockchain that is using upgrade scripts and stable variables in this way. At least I don't know any other blockchain that uses it like Internet Computer does. And one reason for that is that Internet Computer has a very cheap, very cheap storage cost. You are paying with cycles, and every few trillion cycles is going to be even worth a single dollar. So yeah, on Solana and Ethereum, you're going to pay millions of dollars or hundreds of dollars for just a single for 1 gigabyte of data. But let's come back to stable variables. With stable variables, what we are basically saying is that we want Internet Computer to listen to our code. We want it to notice the information that we do want to keep. So yes, we want to keep the hash map database, we want to keep the B3 map database, and most importantly, we are going to want to keep the admins vector. The reason for that is that if we lose the list of our admins, the canister won't work after we reinstall the code, we upgrade the code. So with a stable structure, we just tell to the Internet Computer that this is the list of information that I want to keep before and after the upgrade. I want Internet Computer to guarantee me that these are going to be safe. So Internet Computer says that, hey, you can do it in one way. You have a pre-upgrade method and you have a post-upgrade method. You can use them, you can utilize them. How can you do that? You can do it like this. In about 20 lines of code, you make sure that your data is safe after code upgrades. So the pre-upgrade method is the last method that the Internet Computer Protocol is going to run before it reinstalls the code. You won't run it personally, you won't run it manually ever. This is a method that Internet Computer is going to call itself. So please don't try to call it. I mean, I haven't tried to call it, so I don't know exactly what happens when you try to call it yourself. Probably nothing special. But yeah, I mean, there is no reason to call it yourself. The Internet Computer will do it for you. When you run the command dfx deploy, you are going to tell dfx that the code should be replaced by the new code, and dfx will run the pre-upgrade method before it reinstalls the code, and it will run the post-upgrade method after the code is reinstalled. So basically, the pre-upgrade method just tries to make an archive of every single database that you have in your canister and your admins vector. It will just try to make an archive of them, and it will update the stable storage. Here we are calling the stable store method instance. And we are saying that we want the stable storage to be replaced by these new values. So Internet Computer is going to store the information, and this is the error handling part. It is nothing special here either, but Internet Computer is going to make an archive of all of your data, and it will keep your data in the stable storage. And in post-upgrade, which is the first method that is going to be run after the upgrade, and all of those information inside of the stable storage are going to be loaded again in your own databases. So it will be like nothing happened. Like we didn't lose data, we didn't lose anything during the upgrade process. And that is the magic of upgrade scripts. So here in post-upgrade, notice the macro of post-upgrade and pre-upgrade, by the way. These are very necessary. In post-upgrade, we are going to try to get the mutable version, because we are going to change the information inside of the hashmap DB, and the hashmap DB doesn't contain anything after the upgrade. These are all empty. So when they are empty, you can you will probably know that you should load the new information inside of them. So we are loading the hashmap DB from the stable storage, and we are loading the admins vector. And you have to notice that these load and archive methods are some things that are not inherently inside of the Internet Computer. So I've written them myself. You can just copy these. The case would be probably the same for your dapps too, or you can tweak them. Then so what it basically does is that it takes a hash map and converts the hash map to a vector. As you can see, it replaces the database with a new empty hash map. You see, the new hash map is empty. This self.0, the mutable instance, has information, but it is going to be replaced by new. And this self.0, which already has information, is going to be turned into an iterator, and we are calling the collect method on that. The collect method is just going to actually collect all of the principal IDs, the key values, and turn them into vectors. So this is a very simple task for our canister. We don't have to worry about it. And the load method does the opposite. It takes a vector and changes that vector into a hash map. So as you can see, we are just replacing self.0, which is now empty, with the new information. And that is all you're going to need for your upgrade scripts. What I strongly encourage is taking inspiration from other projects. There are so many awesome projects that are in the Internet Computer space. You can use them, try to read their code. You can learn wonderful things about Internet Computer development from them. I'm just going to mention some psychedelic repositories, because I'm from psychedelic, and naturally repositories that I know best are inside of Psychedelic because we have written them. One of the things that, one of the repositories that you would want to check for data storage is dapps. Dapps is a collection of registries. So when you go to your plug wallets, you see, when I try to go and see my NFTs, these are my cap crowns, and it is dapps that actually gives you the list of the canisters, and it is dapps that makes this connection possible. So this is the app that actually makes it possible to connect to ICP wrapped ICP and cycles canister, and this is Dank actually XCC that records all of your activity. So it is really important to know how these projects work if you're going to utilize them in your own dApp. They have documentations, of course, but if you're going to take inspiration for your own projects from these, you should read the code. So for dApp, you just have to come to registries. This is the collection of deployed registries on the mainnet, tokens, NFT, canister registry, and the address book. This is not deployed yet. It is our next release. So if you go to NFT, you will see something similar. We have an upgrade script, takes information, archives them, adds them to a stable storage, and in post-upgrade, loads them again in nft.rs file. We have an implementation of a certain hash map with principal and NFT canister metadata. The archive method and the load method are basically the same. And if we go to other canisters, the same, you will see the same. And when you go to CAP, for example, CAP is about transaction history. So it's certified assets provenance. You will see all of your transaction history and the provenance of NFTs and tokens and things like that on Internet Computer with CAP. So if you go to cap.oo, you will see that this is the UI for CAP in CAP Explorer. It is going to take a while to load, but you can see all of the transactions that have been made inside of NFTs that are using CAP for provenance and transaction history. For example, every single transaction between Crown NFTs is going to be recorded in CAP. So it is extremely important to make sure that these canisters actually keep their information, because if CAP loses the information, there will be chaos in the NFT community of Internet Computer right now. If CAP loses information, we won't know who is the owner of what exactly, unless the canister itself is, storing them in a place other than CAP as well as a backup. So it is really important to make sure that your data is safe. So CAP is also another canister that you want to read and learn more about information. And the last one is Dank, which is essentially a bank, decentralized bank. These are fun projects to read. We wanted to talk about certified assets canisters as well, but honestly, I don't think there's enough time for it. We are already, we have spent more time on the lecture already than we expected. So if I am going to actually talk about certified assets, it's going to take at least 2 or 3 hours. And I'm not kidding. The certified assets is just that big if you want to completely understand it. But you can read a few documentations, like here we have certified assets canisters. I can't seem to find the documentation right now. I'll send you the link later. But there is also a YouTube video that you are going to, you'd want to watch if you're going to learn about certified assets. I'm going to share that with you as well. It's in Definity's channel. Those videos and documentations are going to be way more complete than any other presentation. If I was going to even give you a presentation about certified assets canisters, and you probably won't need certified assets canisters unless you're actually building something very sensitive, very important in regards of the information. For example, even in dApp, I'm not using certified assets. The reason for that is that if I lose the information inside of dApp, even though I'm not going to lose them because I take care of upgrade the script, but even if I lose the information in dApp, I can just simply add them again. It's just a list of canisters. But if we lose the information in CAP, as I told you, there would be chaos. So we are just trying to make sure that CAP has the most validated and secure information. And the same goes for DAG and XCC. So I'm going to share those resources with you as well. You can use this repository and these code samples in your own projects and take inspiration from them. I'm probably going to end the presentation right here. I've been talking too much, but yeah, I'm going to stop sharing my screen for now.
Thank you very much, Nima, for the presentation. Let's open the stage for questions. If you have any question, please raise your hand.
There was a question in the chat, I remember.
Okay.
So this is a question: what's the difference between CAP and dApp, or is CAP equivalent to a shared instance of dApp? No. Well, these are two very different products. So you are going to use CAP if you want to, record transaction histories. Like if I move my canister, my NFT from my plug wallet to another plug account, it is going to be recorded in CAP. But dApp is just a list of canisters, and their metadata, like this is the principal ID for the Crowns NFT collection, and this is the information about the Crowns NFT collection. The name is Cap Crowns. The description is 10,000 randomly generated, crowns, and this is a website link. This is the, a GitHub link or things like that. But Cap is about transaction histories.
Any other question? Well, it seems that we don't have any other questions, so we can end the session. Thank you very much, Nima, for the presentation, and see you guys in a few hours for the first lecture of the next day, the last day, actually. Thank you.
Of course. Actually, yes, I know who Shahram Nazari is, by the way, Ashton. He's a very famous Iranian singer. Yes, I'm going to share the links in the Discord channel, right?
Yes, you can share them, exactly. You can use the general channel to share the, well, we actually have a channel called Learning Resources, if I'm not mistaken. So you can share them through that channel.
Okay.
Perfect. Thank you, Nima.
Yes.
Have a nice day, guys.
Thanks, guys. Bye.